Now we will be proving a logical equivalence by using algebra of logic. And let's do it by an example. So let's look at showing that this biconditional here, P if and only if Q, is equivalent to P and Q, or not P and not Q. And in a different video, we showed how to do this with truth tables. Here we will show how to do it with an algebra of logic by using logical rules that we have established already. Okay, so let's start by writing the left-hand side. So P if and only if Q. And the idea here is that by the biconditional law, so we saw the biconditional law, we can rewrite a biconditional as two implications. So P if and only if Q is equivalent to P implies Q and Q implies P. Okay, we can then get rid of the implication by using the implication law. So the implication law. And so with that, we saw that P implies Q will be equivalent to not P or Q. So that's the first part. And then you have an and. And then the second part is the Q implies P will be equivalent to not Q or P. So with that, we got rid of all the biconditionals and implications, and we just need to deal with ors and ands and negations. So here, we can then apply a distributive law, where it's essentially applying De Morgan's and multiple times. And so this will act very much like what you would distribute if you were doing sums over, like if this was an addition and this was a multiplication, you're essentially able to distribute these out. And so this will be equivalent to not P and not Q, or the first with the second, right? So not P and P, or the second term with the first of the second part there, which would be a Q and not Q, or a Q and P. So just to go carefully again, essentially I'm saying not P and not Q, that's this part, then not P and P, which is this part, then Q and not Q, which is this part, and then Q and P, which is this part, and I'm doing an OR of all of them. Okay, now we can apply essentially, in this case we have two contradictions. So we saw, if you pay attention here, not P and P, this will always be false. This is a contradiction. Same for Q and not Q, because it can never be the case that they're both true, right? And that's the only way for an and to be true. So if P is true, not P is false. And if P is false, then not P is true. But if P is false, this will just be false anyways. So in other words, you can rewrite this as not P and not Q, or then this part is a false, or something that is always equivalent to false again, or Q and P. Well, when you take an or, so you can simplify, when you take or of false, you can just get rid of the false part, because the false will never, so anything, so you can think of it like this. So true or false will be always true, and false or false will be always false, which means that it doesn't matter what the first thing is. So every time you take a proposition, and you OR it with a false, this should always be equivalent to the proposition itself. So that's the idea that we're using here to simplify. So that means that the falses, you can throw them away. And so you get not P and not Q, or Q and P. But that is essentially what we were trying to show. So Q and P is just the same as P and Q. And then you have the OR here. And then you have not P and not Q is just not P and not Q. So these are the same. So this is just the right-hand side of what we wanted to prove. And so with this, we have proved the equivalence by rewriting it by using algebra of logic instead of using a truth table.